Okay, now let's just recall a bit about what we learned for electric field before this. If let's just say I told you that you have an isolated charge, which is just a single charge that is far away from any other charges, is isolated in space. Say this one is your isolated charge with charge big Q here. If I were to ask you to draw the graph of variation of electric fields, if I were to ask you to draw the graph of variation of electric potential with distance x from the center, let's just say that this one here from the center of the sphere is x. If I ask you to draw the variation of electric potential versus distance, what you have learned before this is that inside the sphere, the potential should have been constant. And then after that, outside the sphere, the potential will tend to decrease in this manner. Okay, so this one was basically inside your sphere. And then this one was outside your sphere. Okay, so this is the graph of potential versus distance that you expect to see for an isolated charge. But if let's just say then we move on to another different case where I tell you that now you have two different charges and you are interested in the electric field strength, you're interested in the electric potential between the two charges along this yellow line here. That time it was already derived for you that the potential at any point between the two charges would be Vp equals to VA plus VB, such that if you were to draw a graph of variation of electric potential versus distance x again, like the one that I just did before, what you expect to see is a graph that looks like this. Just give me a moment when I draw it out. You expect to see a graph that looks like this now. Something that looks like this. Okay, so here, if I were going to ask you about potential, if you recall what potential was before this, potential is actually the work done to bring a charge from infinity. Sorry, it's the work done per unit positive charge to bring a charge from infinity to a point inside the electric field, right? So if you are inside an electric field and I were to ask you the value of potentials at different points inside the electric field, potential values tend to vary at different points in the electric field. This one we already know. Now, from those variation of potentials inside your electric field, you could actually deduce out the electric field strength at that particular point, okay? So to do that, you have to make use of a certain quantity called potential gradient. Potential gradient at a point in a field is actually the change in potential per unit distance. This particular quantity potential gradient will actually allow you to find out what is the field strength at a particular point. So how do you go about in doing that? You can just consider a very simple case. Now, before that, when you say potential gradient is change in potential per unit distance, it just simply means this. It is delta V, potential difference between 2 points, divided by delta X, the distance between the 2 points, okay? So if you want to see the relation between potential gradient and electric field strength, you just consider a simple case first where you have a uniform electric field of field strength E set up between two metal plates X and Y, which are separated by distance D and have a PD of delta V between them. So these are your charge parallel plates, okay? And between the plates, you have a separation of D and a potential difference of delta V. So let's just consider that you put a positive test charge inside the field and you let it move. Here is mentioned that you have a small charge positive Q that is being moved from the positively charged plate to the negatively charged plate such that the work done, W, is given by Q delta V. So you imagine this now, if you have a positively charged test charge, you put it at the positive test charge here, you put it at the positive test plate here, it will have a tendency to move downwards towards the negatively charged plate, okay? So the electric force acting on the positive test charge is actually supposed to be downwards. That's the reason why it actually moved downwards in the first place. Or you can actually also think of it this way. Because this is positive test charge and this is positive plate, there is repulsion here. And then because this is positive test charge and this is negative plate, there is attraction here. So by right, that test charge is supposed to move downwards, okay? But there's also another way to look at it. There's also another way to look at it to know that the electric force acting on the test charge is downwards. This one is through what I mentioned to you earlier last time early in the lesson. I mentioned to you that number one, direction of electric field is from higher potential to lower potential. So this one, direction of electric field is actually, I believe, in the first page of your notes. Direction of electric field is from higher potential to lower potential. And then after that, there's also something that I mentioned about the relation between direction of electric field and direction of force on the positive test charge. That one being that direction of electric force on a positive test charge always follows direction of the field. Okay, so let me rewrite this. There's not enough space here. The direction of electric force on the positive test charge always follows direction of the field. Okay, so keyword here is positive test charge, and that the electric force acting on the test charge must always follow direction of the field. So let's just look at the example that we have here for the charge parallel plate. Plate X, the plate above here, is actually positively charged. This one is considered to be higher potential. Okay, but the plate Y, the plate at the bottom here, this one is negatively charged. This one is considered to be lower potential. So right now, based on point number one that I wrote here, where I mentioned that direction of electric field tends to follow the direction from higher potential to lower potential, this will actually tell you that your field strength direction is supposed to be downwards. So your E is supposed to be downwards. And then now you go and put a positive test charge. So based on statement number two, if I already know the direction of the electric field, and I already know that this is a positive test charge, it follows that the direction of my electric force on the positive test charge must be following the direction of the electric field. So it therefore must be pointing downwards. That's how I know it will move downwards here. Okay. So when you are moving downwards, you have a force that is being applied to that positive test charge, and it moves a certain distance d. So there must be work done here. So if you recall in your AS, when it came to the work energy power chapter, if you wanted to find out work done, you can actually use force times distance move. So there were a few conditions to that force there. The first one being that the force must be constant. Second one, it must be an applied force, not resultant force. And then the third one is that that force must be in direction of distance move. These were the three things to remember when you wanted to use the work equals to FD equation. So here of interest to you is the fact that you need to have constant force in the first place in order to be able to use this equation. Now, in your case, remember what I told you before, for charge parallel plates, you will always have uniform electric field strength. Uniform here already means constant electric field strength, okay? So if you recall the equation for electric field strength being E equals to Fe over Q, such that Fe is QE, if your Q is constant, your charge never change, and your field strength here is constant, so the obvious conclusion would be that the electric force must be constant here. So your electric force acting on your positive test charge would be constant throughout the field, throughout anywhere between this region here. Okay, it will be constant as long as it's in between the charge parallel plates. Okay, the force acting on that positive test charge would always be constant. So you know you can use the work equation equals to force times distance move. Okay, so that one is actually number 2 here. All right, this is equation number 2. Now for equation number 1, where I told you that the work done is equals to Q delta V, this one actually came from what we did last week, or in the last 2 lessons actually. That time I mentioned to you EPE is actually Q times your potential. This is for at a point only. But if you want to find the change in electric potential energy between 2 points, it's actually Q times delta V, or Q times the potential difference between 2 points. This is between 2 points. So the thing here is that what you also know from the work energy power chapter is that work done is used to change the energy of an object. This is also what you've learned under the work energy power chapter of AS. So here, although I say change in electric potential energy is actually Q times the potential difference, it's also correct to say that this is also work done. The amount of work that I've done to move the charge from one end of this plate here to the other end of the other plate is going to be equal to the charge times the potential difference. Okay, so now I have two equations for work done, this first one and the second one. So what I want to do now is that I want to equate both of them together, so that now I get Q delta V equals to Fe times D. And then after that, I rearrange this so that I get Fe over Q equals to delta V over D. Now, since field strength is actually force per unit positive charge, this one would automatically be equals to E already. So that now my E is actually going to be delta V over delta D. Now this delta V over D is actually the potential difference between the 2 points divided by the distance between the 2 points. This one is actually my potential gradient. Okay, so it's from here that we eventually come to some sort of conclusion saying that when we are talking about electric field strength at any point, the electric field strength is actually the negative potential gradient. In other words, summarized in equation form is actually this one. Okay, now you may be wondering, why is there suddenly a negative sign here? The negative sign is actually more to indicate direction of your electric field. That is always from higher potential to lower potential. Okay, the negative sign here indicates to you that the direction of the electric field is always in the direction of decreasing potential. Recall the point number 1 that I just wrote on the right hand side here. Direction of electric field is always from higher potential to lower potential. It also means that your electric field is always in the direction of decreasing potential. Okay, so you look at this equation here, field strength equals to negative potential gradient. This delta V over delta X here gives you the magnitude of your electric field strength. But the negative here gives you the direction of your electric field strength, in that it is always in the direction of decreasing potential. Okay, so this is how you can actually find field strength from potential. You need to know the potential gradient, only then can you find out the field strength. Okay, so let's just look at a few examples here. If, say, for example, you have a charge parallel plate, you look at the bottom part of your notes, okay? So you look at, for a case of charge parallel plates like the one that you've just seen, let me just erase whatever you have here. If you're talking about a case of charge parallel plates, for charge parallel plates, I already mentioned earlier that they always tend to have uniform electric field or constant electric field. Now, when they have constant electric field, the potential between the plate tends to change uniformly with distance from one plate to another. So what do we mean by that is that if you look at the charge parallel plate below here, okay, these are your charge parallel plates, your potential would tend to vary between the plates, okay? The variation of potential with distance will be such that your V is increasing from the bottom plate to the top plate. It tends to vary with distance, okay? If you were asked to draw a graph of potential versus distance for a charge parallel plate, the variation of your potential with distance would tend to be linear, such that you get a straight line like this, okay? It cannot be a curve, it cannot be anything else. It must be a straight line, because when you see that here your potential is 0 volts, and then after that it increases to 12 volts. Sometimes people have they understand that potential tends to increase with distance here. If let's just say this one is where I measure my distance x, my potential tends to increase, but there could be a few variations. Either it's a straight line, or either it's a curved line like this, or a curved line like this. So which one is actually the correct one? The correct one should have actually been the middle line here, the one where the line is straight. The other two is actually wrong. So how do I know that it's going to be a straight line in the first place? Is due to the fact that field strength is potential gradient, okay? Now, if you look at the graph of potential versus distance, like this one here, the gradient of your graph, meaning to say this one, is going to be delta V over delta X, isn't it? So delta V over delta X is actually your field strength, okay? So in your case, for charged parallel plates, we already know automatically it's going to have constant electric field strength. So we know that if E is constant, the gradient must be constant. Therefore, it's going to be a straight line, okay? So variation electric potential with distance for charged parallel plates must always be linear like this, okay? Now, if let's just say you were given some values and some distances for charged parallel plate, if you were to try and test a few points to find out the electric field strength at those different points, you will eventually get back the same answer for field strength. Say, for example, you look at the left working here. If you're trying to find the field strength between the top and bottom plate, meaning to say you're trying to find the field strength right over here, you take the potential difference between those 2 points, and then you go and divide by the distance. You get 12 divided by 6, you get 2 volts per centimeter. If let's just say that you're interested in finding the potential gradient somewhere midpoint, somewhere at the midpoint here, say here, you find the potential difference between the midpoint and the bottom plate and divide by the distance, is going to be 6 divided by 3, giving you 2 volts per centimeter also. So even though you have changes in values here, the end result is that your field strength should still be the same, okay? So that's just one thing to note. Okay, then after that, you look at the last page, okay? So for isolated charges that have non-uniform field, your potential doesn't vary uniformly. That one is only for charged parallel plates. Okay, here, this one here, they say isolated charges have non-uniform field. Your potential doesn't vary uniformly. It tends to follow an inverse square relation where E is inversely proportional to separation squared. That one is actually related to the equation that I wrote on the left-hand side here. Remember, for isolated charge, the potential at any point is actually equals to 1 over 4 pi epsilon naught Q over R. So from that graph alone, you can actually see that potential versus distance is going to be following this kind of relation. So that if you were to plot a graph of potential versus distance, it should be following a exponential decay curve like this. Okay, so yeah, there's one mistake here that I just noticed in my notes. This one I'm talking about potential, right? And then I say it follows an inverse square relation. This one is E proportional to R square. This one I think should have been V inversely proportional to R. Okay, somehow or another I say potential, but I go and wrote field strength here. This one is actually supposed to be potential. V is inversely proportional to R. Okay, so if V is inversely proportional to R, this is the graph that you're supposed to get. Okay, now from that graph of potential versus distance alone, you will actually be able to find out how does your field strength vary. Okay, that one is again by looking at the gradient of your graph, specifically the gradient of your tangent. See, if I look at the curve here for field strength versus distance, sorry, for potential versus distance, I look at how the gradient changes. You'll notice that your gradient here tends to decrease. And because gradient here is delta V over delta X, meaning to say it's your field strength, since your gradient is decreasing, this would mean that your field strength is actually decreasing. Okay, so this is how you can actually deduce out from your graph of potential versus distance how your field strength changes. Okay. You also did learn an equation that tells you how field strength changes with distance. That one being equation E equals to 1 over 4 pi epsilon naught Q over R squared. If you were to plot a graph of field strength versus distance now, you will get an exponential decay curve that looks like the one above. Now, when R increases, your field strength decreases. This is consistent with what you're seeing above, okay?